Final or initial? Yes. I'm not sure exactly what the question was. Okay. Let's keep going, and these will become clearer. Okay, so now I've sort of been tricking you. We've kind of been talking about a specific kind of motion, and we kind of haven't. Okay? I keep drawing something going in a circle. I've maybe implied that the velocity was constant, but now I'm going to tell you. We're going to do uniform circular motion. This lecture is going way too smooth because I haven't written my number up here. There you go. Let's see. So the question is, gravity affect centripetal acceleration? That totally depends on which way you're moving. But we're going to do some problems like that before this lecture's over. Why is it v sub t in the acceleration formula? Because in general, it's because v1 and v2 is a constant magnitude. Right? If we're now doing uniform circular motion, v1 equals v2 magnitudes, and that magnitude is usually called vt, the tangential velocity. You don't have to write the t every time, as long as you know what it is and don't get confused. Okay, uniform circular motion really is the motion I've been drawing. It's just constant vt. Right, the magnitude of that velocity is constant. I didn't say it was, I didn't say it wasn't. Kind of implied that it was. Right, but now I'm saying if it's really constant, that's uniform circular motion. Right, so let's look at some uniform circular motion. Here we go. See the little red dot? Here it goes. Uniform circular motion. Is it perfectly uniform? Not really, because it's slowing down, isn't it? I can't make it perfectly uniform. What is the W in the equation of tangential velocity? That's omega. That's omega. Because over here we said at the very beginning, angular velocity is how fast around is omega. So it's a lowercase omega. Uppercase omega looks like that. Lowercase omega looks like that. If I draw a W, I draw it like that, except I go really fast and I draw it like that. So you can't tell. I try to make my omegas very loopy. And I just don't draw W's in general. Not that kind of guy. So uniform circular motion means the velocity is constant, and it also means, one way to think about it is the centripetal acceleration is the only acceleration. We'll talk about cases where something is not in uniform circular motion, and it's because some other force is messing with it. Like here, friction is messing with it, and the acceleration is not exactly centripetal. But for now, uniform circular motion, it's centripetal. Here we go again. Something going around some circle with radius r. It's going at some tangential velocity that's constant. We don't need to put the bars on there. And it's got some centripetal acceleration coming in. Okay? What we're trying to do is build up more and more parameters to think about. We're almost done. So we had those three: position, theta, omega, alpha. Then we have these three: arc length, tangential velocity, centripetal acceleration. That's really all you need, except problems often give you the period. Period t. T is the time for a complete circle, in SES. That's S for seconds, right? It's in seconds. So a problem will say this thing goes around in 30 seconds. That's the period. So we want to show you the formulas with the period in them. Okay? It's less likely that they'll give you the frequency, but they might. And that's just basically, in this case, it's circles per second. How many? The number of circles per second. And it's in hertz. And hertz are 1 over seconds. So, and it's big L, it's little f. So the simple relation is just f is 1 over t and t is 1 over f. Okay, but usually these are really the exact same information. Okay, they're not different. So we'll say that f equals 1 over t. And we'll say that's a formula, but I'll point out that this is not some fundamental property of the universe. This is the same info. It's just a problem might give you one or the other. That's all. Okay? That's not the important thing I want to show you. What I want to show you is how we now write these in terms of this thing that most problems are written in terms of. Okay? So instead of this calculus-based tangential velocity where we took a derivative of the arc length, which is a little unfamiliar, for uniform circular motion, let's just calculate it, right? It's how far it goes over how long it takes. So how far does it go? One circle is all the way around, also known as the circumference, also known as 2 pi r. And how long did it take? It took the period. So that's another way to figure out the tangential velocity. in a problem, if you're told how big the circle is and you're told how long it takes to go around, then you just imagine it going in a line, and it's just delta x over delta t. And if you notice, if you're really paying attention here, you say, wait a minute, look at that. What is that? What was 2 pi over t? That must be omega. I know that's omega, for one thing, is I know that Vt is omega r. Right up here, Vt is omega r. This thing must be omega. And does it make sense that that's omega? Yes. Because it's basically going through an entire 2 pi radians, an entire circle, and how long does it take? It's the radians per second. Right? So you can see it sitting right in there. Okay. So you can see then what we've said is Vt is omega r. Well, we already knew that. Right? That's from calculus. So you get the same thing. And then again, the centripetal acceleration I'll just give you. We won't prove it. Oh, we could just substitute here. Right? If Vt is omega r and the centripetal acceleration is Vt squared over r, then it's omega squared r squared here, and one of the r's goes away. So it's omega squared r. Yeah. The centripetal acceleration. So that's really all the, these are just new relationships, right? The new values you care about are the period and the frequency. And these are some relationships between them. And a lot of these relationships are redundant, like I said. I mean, saying this is the same as saying that. It just depends on what problem you're doing. Do you have the period, or do you have the angular velocity? Okay. Let's see. Now we're going to do a sample calculation in our final minutes. Oh, it's going to be fun. This is going to be the greatest. Let's say the end of a 120 millimeter minute hand. I set up this clock at the beginning of the semester for this demonstration. Okay? See that minute hand. It's 120 millimeters. I measured it. And we're going to calculate the following. T, F, theta, omega, alpha, Vt, and AC. Everything we've talked about. Let's calculate for a minute hand. And let's do it in 1 minute. What do you say? Oh, we only have 1 minute to do this. Okay. What's the period? In seconds. 60 seconds. Is that how long it takes a minute hand? Oh, wait a minute. The minute, that's a second hand. Oh, shit. Wait, what did I do? This is the second hand. Wait. Yeah, the second hand. All my numbers are for the second hand. The period of the second hand. What's the frequency of the second hand? 1 over 60, 0.0167 hertz. Or you could put inverse seconds if you want. What's the angular position of the second hand? The current time. I don't know, right? It's moving, right? The angular position is changing all the time. So right now it's 45 degrees, depending on how you define 0 and which way is positive. What is omega? The angular velocity of the end of the second hand. I said the end because some of these are going to be translational velocities, right? Well, we have the period, so I would use, what did they ask for? I would use this idea, that omega is 2 pi over t. Right? So omega is 2 pi, goes through 2 pi radians in what? 60 seconds. All right, so blah, 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 0.105 radians per second. So you can see this is just plug and chug. You just got to realize what number means what. What's Vt? What's the actual speed of the end of that second hand? How fast is it going? We could do this. Or now that we have that one, we could do that. Now that we have omega, this is the more direct one, right? It's 2 pi. What's the radius? 0.12 meters. Over what? Over t? Yeah, over t, over 60 seconds. How fast is it going? 0.0126 meters per second. That sounds pretty slow, but meters per second is pretty fast, right? I mean, that thing is not moving anywhere near a meter in a second. It's moving a teeny bit in a second. So what's that? It's like 1.2 centimeters per second. That's believable. We could say, okay, let's do it the other way. What's Vt? It's omega r. What is omega? 0.105. And what is r? 0.12. 0.1 times 0.1 is about 0.01. Right? So sure enough, it's about the same thing. So these formulas are consistent. What do you know? What about the centripetal acceleration of something on the end? Oh, it's just v squared over r, right? So it's just this v, 0.0126 squared over 0.12. And I don't know, it's 0.0013 0.32 meters per second squared. You can check your work. Okay. So we're just plugging in. And I'll leave as an exercise for the reader this one. Plug this one in, you'll get the same thing as what I got from v squared over r, because it's the same thing. These things are not really different from each other. Okay? Okay, so what we're going to do now is take our break, and I'm going to show you one thing to look at here. And y'all can see if you know what it is. I think you're going to know what it is. Oh, no. No, no. There we go. It's not this exciting, so please talk amongst yourselves. Okay.